COVID-19 pandemic has brought many changes to our way of life. In hospitals, doctors and nurses rely on dwindling supplies of personal protective equipment, including gloves and masks to keep themselves and their patients safe. Unfortunately, hospitals have seen an uptick in PPE-related thefts of glove boxes, hand sanitizers, masks, and more. That's why we built MedTrack, a system that combines vision information from CCTV cameras and signals from RFID tags to detect and track people stealing PPE from hospitals. The system works by tagging assets with RFID tags. With an RFID reader and a camera by an exit point, the system can identify which people are leaving the building with PPE and notify security if a theft is occurring. Our data pipeline has three main stages: collecting, processing, and matching. We capture vision data from our video camera and RSSI information from our UHF RFID reader. With the camera image, we first find a person in the frame, then estimate the person's depth within the given bounding box. Using this, combined with RSSI data, we make an inference as to which person is holding which tagged object. For the vision-based detection, we use the popular YOLO library along with the deep sort tracking library to identify and track a person over time. Given a bounding box from those libraries, we run a depth estimation over the bounding box to gauge the depth of a given person.
After collecting video and RSSI measurements for several trial runs, we saw that our data was very noisy. In this plot, we can see that in the raw data, a given depth estimate can correspond to many different RSSI values. This is clearly an issue if we intend to match the RSSI values associated with tags to the monocular depth estimates associated with people. To address the noise in our data, we did two things. First, we applied a moving average convolution, which eliminated outlier data points. Second, as you'll see when we later discuss our inference approach, we reduced noise by considering how much RSSI and monocular depth estimates change across small time periods, in this case, k time steps. This enables us to make matches between people and objects based on relative motion, as opposed to absolute motion, which is subject to higher noise levels. We can visualize the effectiveness of our denoising techniques with a side-by-side of the original noisy data and the denoised data. After denoising, a more linear trend begins to appear. As changes in depth increase, so do changes in RSSI. This pattern was invisible before denoising. Equipped with a workable dataset, we began to solve the problem of object tracking with a binary classification algorithm. To do this, we assumed a restricted environment. 2 users, 2 tags, that's it. We matched the near person with the near tag and the far person with the far tag, mapping the smaller RSSI value to the greater depth estimate. This worked well when there were obvious depth differences between people, but it didn't capture lateral movement well, and it did not generalize to higher traffic environments with variable numbers of people and tags. In an effort to find a solution that worked well in variable traffic environments, we designed an inference procedure that builds a similarity score between RFID tracklets and camera-based depth tracklets. This approach does not impose strict assumptions on the environment, and it captures the many-to-one property that characterizes the problem of object tracking, because a similarity score is computed for every person-object pair. This means multiple objects can be mapped to the same person, a very probable occurrence in the real world. If a person and an object are moving in a similar way, it is likely that the person is carrying the object. Our similarity score is designed to pick up on this. It gauges the distance a person is from the camera using monocular depth estimation, and it gauges the distance an object is from the camera using the RSSI value. To make our metric more robust, we also considered the motion of people by measuring how much the centroid of their bounding box moved across time. As you can see in our similarity function, we compute correlations between changes in bounding box coordinates and RSSI, and between changes in estimated depth and RSSI for a particular person-object pair. Multiplying these values by a set of weights, we produce a final similarity score. We then associate each object to the person who produced its highest similarity score.
Following our construction of the initial inference procedure, we decided to tune the denoising parameters discussed earlier to better construct an efficient and effective data processing pipeline. Shown below is the Pearson correlation coefficient for camera and RFID data from the same person for different moving average parameters and different data value skips. We chose parameters that required the least amount of raw data to minimize the end-to-end latency of the system. Informed by the correlation matrix shown here, we chose a moving average parameter of 20 time steps and a data value skip parameter of 8 time steps. Here you can see our implementation with tuned parameters for denoising in action. Note that if RFID or YOLO output is unavailable for a given frame, the matching algorithm returns no matches.
To quantitatively evaluate our results, we compared the match tag numbers with the ground truth information about tags that we stuck onto the boxes. Although our theoretical approach attempted to denoise the data, much of it proved too difficult for the system to overcome, resulting in relatively frequent none readings.
We also experimented with 2 machine learning-based approaches to matching, both of which we will discuss. The first pertains to building a more accurate similarity score by learning a nonlinear function of the input data. The goal, in the simplest terms, is to learn a similarity score across all possible combinations of RFID tracklets and camera and depth tracklets for a given number of time steps. Time steps where the RFID data matches the camera data should yield a high similarity score, and vice versa. In building our training and validation datasets, we use 20 consecutive time steps of data for a single input vector. The data is fed through ReLU layers of dimension 100, 80, and 40, and a sigmoid activation layer with a single output between 0 and 1, the similarity score. We engineered our training approach to account for the time and resource constraints in data gathering. Practically speaking, our training data consisted of 1 or 2 people walking with a few items. With very few raw matchings in the training data, we had to negatively sample the dataset for mismatching tracklets. We additionally noticed that our matchings are binary, while similarity scores are continuous. If we only choose entirely positive matches with score 1, or entirely negative matches with score 0, the model wouldn't train well to output the continuous similarity scores. As such, we also include vectors where tracklets are temporally close to each other, and assign a Gaussian label that reflects the time-step difference between the tracklets. We trained the network for 30 epochs with the eta delta adaptive learning rate and a mean squared error loss, until we achieved favorable testing and validation losses. Using our trained neural network, we computed the similarity score for vectors constructed with camera tracklets and RFID tracklets from different time steps in a given sample video. The figure on the right is a heat matrix depicting the scores with the RFID time step plotted against the camera and depth time steps. Light value indicate higher similarity scores, and vice versa. Note that while noise persists, we see a linear yellow line in the matrix, indicating a high similarity score for camera, depth, and RFID tracklets where the time steps match, lending credibility to the approach. We originally considered another ML approach, but network training yielded unfavorable results. The approach involved recognizing that the matching was a bipartite matching between RFID and camera tracklets. We attempted to discretize the movement space from RFID and camera outputs, co-embed the RFID and camera movement vectors into the same latent space, and perform a nearest neighbor search on the embeddings. Specifically, we used a variant of an autoencoder, where the training data was a vector of either the RFID or the camera depth tracklet, and the label was a vector of both tracklets. The idea was that because the network was tasked with constructing both tracklets from a single tracklet, it would learn a lower dimensional representation where matching tracklets would be close in the latent space. We ran into challenges when creating the embedding, and decided to go with the previous approach.